We're back with chapter 4. We're going to do a few more examples. These are examples for section 4.5. Again, this chapter is on the Bernoulli equation and pressure variation. We're going to skip forward to section 4.5 to remind you that this is the section on Euler's equation. We developed an equation for Euler's, or developed the Euler equation, and this is it. We're going to use it in a couple of different problems. And there are a couple of examples to do. And basically, this is the scalar form, which we will use today. And then in general, this would be the gradient in 3 dimensions of how the pressure varies in x, y, and z. But in our case, we'll be able to define some paths, or L, along which we have acceleration, and then we'll be able to apply Euler's equation to those along those paths. So let's just skip forward here to the examples. We're going to first start with example 4.2. We're going to apply Euler's equation to a column of fluid that's being accelerated upward. The statement of the problem shows that a column of water in a vertical tube is being accelerated by a piston in the vertical direction at 100 meters per second squared. So here's basically this piston is being accelerated upward at a constant acceleration. The depth of the water column is 10 centimeters, and we're going to assume that the fluid is incompressible. Because we don't want, when we push on this thing hard with 100 meters per second, we don't want the fluid to squish and change this dimension here. So we're assuming that it's incompressible, which we know for most fluids is a very good assumption. And we want to find the gauge pressure on the piston right here. Now, we're in a good situation because we already know the gauge pressure at the top. We're going to assume that that's atmospheric. And we're going to assume that this thing doesn't go up so far that the pressure changes, the atmospheric pressure changes appreciably. So if we just go up a meter or two, it's not going to matter. That's going to be insignificant. And we're going to assume that the density of water here is 1,000 kilograms per meter cubed, which is standard. So let's go ahead and apply Euler's equation. So basically our situation is that we have this piston accelerating upward, and we want to find the pressure on the fluid here at the piston. So we know we're going to have some acceleration to deal with, but we also know that we have some pressure due to the elevation of the of this fluid above the piston. So let's go ahead and make a plan here. Our plan will be to apply Euler's equation, apply Euler's, whoops, getting ahead of myself, Euler's equation, and this is going to be in the z direction, upward. We're going to have to integrate Euler's equation. Integrate, and this is going to turn out to be pretty easy to do. It's an easy integration between basically from point 1 to point 2. This is the base of the piston. Point 1 is at the base of the piston to the top, because we have to account for the piezometric pressure basically in this. So, and we're going to make some assumptions, which we've already talked about, but I'll list them here. We're going to first assume that the acceleration in the z direction is constant, that we're applying a constant 100 meters per second. We're going to assume that incompressible fluid. Incompressible fluid, and I'll just say incompressible. And we're also going to assume that we have inviscid flow, so there are no viscous effects. So there's no shear stress along the sides of the, there's no shear stress along the walls here of the piston. And that's probably not a great assumption, actually, but we're going to go ahead and assume it just to simplify the problem. And so really what we need to do here in the next step is we need to set up the equation. And so we know we have Euler's equation in general. Let's use the partial derivative. Is the partial derivative along the path of P plus gamma z. This is our piezometric pressure that we've been dealing with all along. And this is minus rho times the acceleration in the L direction, as we saw before in the equation that we just saw in the notes. But in our case, we only have the acceleration changing in one dimension, so we can make that into a total derivative of the pressure plus gamma z equal to minus rho and a in the z direction. So we can rewrite this equation by moving the dz to the other side. We get this equation minus, and so we can integrate both sides. dp plus gamma z, and this is going to be the integral from point 1 to point 2 of minus rho a, whoops, let me just make that a look more like an a z dz. Now this is actually pretty easy to integrate because we know that we're just going to get p plus gamma z. We're going to have to evaluate that at both locations. Put a bracket around this. And since we've assumed that the acceleration is constant, we know, and also it's incompressible flow, we're not going to have any significant density variations. We can pull that out. We can pull both these out front, and we're left here with just z2 minus z1. So if we write this all down now, we're going to have p1 plus gamma z1. Take that back. That's going to be p2 plus gamma z2 minus p1 plus gamma z1, just evaluating this piezometric pressure at both of these locations. 2 minus 1, get the sign right here, that's going to be important. And this is going to be equal to minus rho times this acceleration, the 100 meters per second, z2 minus z1. And so remember that we're going to assume, another assumption is that we're going to, the fourth assumption is we're going to set, I guess we would, this maybe not be an assumption, but we're going to set P2 equal to 0 gauge. So in this case, this goes out. So let's write this equation. We kind of reformulate everything. We have a minus P1. We have plus gamma of Z2 minus Z1 on the left-hand side, and that's all going to equal minus gamma a z of z2 minus z1. So let's move this term over to the other side just by subtracting it from both sides, and what we're left with is minus p1 equal to minus rho az z2 minus z1 minus gamma of z2 minus z1. And let's just multiply through by minus 1, gets rid of all the minus signs. And let's consolidate this thing a little bit. So we're going to have P1, P1 is going to equal rho AZ plus gamma times Z2 minus Z1. Now, note that we can make one more simplification. Since we are interested, we don't actually know gamma, right? But we do know that it equals rho times G. So gamma, let me give myself a little bit more room, equals rho times G. So this is going to imply that we can rewrite this equation as this. Rho of AZ plus G times Z2 minus Z1. So this is interesting. What we see in this equation is that basically the acceleration on the piston at point P1, the pressure is going to depend on the acceleration we're imposing on the piston plus the acceleration of gravity, which makes physical sense to us. So let's go ahead and just plug in here. Plug into this equation. So P1 is going to equal rho, which we're given as 1,000 kilograms per meter cubed. And we have the acceleration plus the acceleration of gravity, G. And these are going to be multiplied by Z2 minus Z1. And if we look way back here, that is just our 10 centimeters or 0.1 meters. So this is going to be times 0.1 meters. So if we do this, we get a value of this many, the numbers give us this value. We can see that, in fact, the acceleration of gravity here is really just a small part. Mainly, the 10,000 is kind of coming from this term here, and the 900 is really coming from this. This is actually, to be more precise, we could have written this as 10,981. But this is, to our significant figures, this is right. But let's go ahead and work out the units now. And so what we see that we get for units is we're going to have a kilogram over meter cubed. We're going to have a meter per second squared, and we're going to have another meter. Yes, so this is going to give us, if we combine this into a kilogram meter second squared, we know that that is a Newton, and we're left with 1 over meter squared. Basically, this guy cancels one of these, and we're left with 1 over meter squared. This is 10,900 newtons over meter squared, which is a Pascal. And so we can simplify this to be equal to 10.9 kilopascal in SI units. So that's quite a pressure, almost 11 kilopascals at the piston, when we know that this pressure up here is actually 0 gauge. And that is a gauge pressure. That is gauge, because we assumed that at the beginning for our P2. Okay, so let's move on to the third problem, which is a two-part problem. And here we're going to determine the pressure at basically this point, the maximum pressure in a tank of in a tanker trailer here. We're first going to apply Euler's equation to the top boundary, along the top boundary, because this truck is decelerating. You can see we're going to apply Euler's equation to gasoline in a decelerating tanker. So we're going to find the pressure first here, and then using that pressure, we're going to find basically the hydrostatic. We're going to add the hydrostatic pressure here, and we're going to get the pressure at the bottom corner. We're assuming, note, that this corner at the top of the fluid and at the back of the truck is 0. That's going to be 0 gauge. And that'll allow us to solve for the first part. So the problem statement is that we have the tank on a trailer truck is completely filled with gasoline, which has a specific weight of 42 pounds per foot cubed. The truck is decelerating at a rate of 10 feet per second. So 2 parts. If the tank on the trailer is 20 feet long, and if the pressure at the top rear of the tank is atmospheric, so we're going to assume that's P equals 0 gauge, what is the pressure at the top front? Okay. And then the second thing, if the tank is 6 feet high, what is the maximum pressure in the tank? And we know that that's going to have to be at the front here, because we're going to have the combination of the deceleration of the fluid basically piling up here, and also we're going to have the hydrostatic pressure of the overburden of the 6 feet on top of it. So it's a 2-part problem, and the first part, our plan is to basically apply. Oops, let me get a pencil. Our plan is to apply Euler's equation to the top of the tank. We're going to use that pressure. This is going to give us a pressure at the front. We're going to use that to, in the second part of the problem, apply Euler's equation a second time to find pressure at the bottom front of the tanker trailer. Okay, so let's go ahead and start out here. So we're going to use the familiar equation here for for part A. We're going to have that Euler's equation equals this: P plus delta Z, and this is going to equal minus rho A along the L direction. This is just our familiar Euler's equation. But in this case, Z is constant, so it's not going to depend. Again, this is along the top of the trailer truck. We're going to go along the top of the trailer truck. Since it's decelerating, we're going to have a pressure here from the deceleration of the fluid. And so this equation, if we write it just in the L direction, oops, let me go get my pencil. This is just going to be the change in pressure along L, because Z, this term is going to cancel out. There's no change in Z, and that is going to equal minus rho times the acceleration in the L direction. And we can then rewrite this as dP equals minus rho AL dL. And if we integrate this from the front to the back, point 1 to point 2, let's say, where point 1 is at the back and point 2 is at the front, and this from point 1 to point 2, and this will be along the length of the truck, we will get out of this P2 minus P1, and this will be minus rho alpha. As long as the truck is decelerating at a constant rate, we'll get L2 minus L1, which is really just the length of the truck. Remember that we're assuming that this is at atmospheric or gauge pressure at the back of the truck. So pretty easy to solve for P2 is going to be minus rho A along the deceleration times basically 20 feet, which is the length of the truck. So plugging in, we're going to use the fact that we know the gamma of the fluid. This is going to be minus gamma over g. And we'll use our acceleration rate, which is 10 feet per second squared, and this is going to be times 20 feet. So our gamma, this is minus 42 pound force F cubed, feet cubed. This is going to be divided by the acceleration of gravity, which is 32.2 in traditional units is this foot second squared, and that's going to be multiplied times 10 feet per second squared, the acceleration, the deceleration of the truck basically, times 20 feet. I can squeeze that in there. So we can see in terms of the units now, these units are going to cancel these units because they're both in acceleration, and this is going to cancel one of these. So our final units are basically pounds per square foot. This is going to be a pound force over foot squared. This is a PSF, pounds per square foot, gauge again. And our the value of this is minus 261. If we multiply out all the and divide by and do the math basically. So that is the pressure at the top of the tank in the front of the truck, of the trailer. Now let's go ahead, let's go back to our picture. So we know now that this is 0 PSF and this is 261 PSF, but we want to find the maximum pressure in the trailer to make sure the trailer is built to withstand this pressure. And so we will need to calculate the overburden basically of the fluid here. We need to use, this is 0.1 now and this is 0.2 to find the pressure at 0.2. So let's go do that. That'll be the second part of our problem. So problem point B, or part B, is we're going to apply the equation again. And in this case, we'll start with Euler's equation again. P plus gamma z equals minus rho AZ, acceleration, and this will be, so that's the equation. But we note that, actually that should not be a z, that should be an L. But we note that this is all in the z direction, and that in fact we have no acceleration. The trailer is not accelerating up and down, it's only accelerating, it's decelerating to the left in the picture. So this actually equals 0. The acceleration, this term right here equals 0. So that makes it very easy. Again, our L direction now is in the z direction. So we're going to have this situation here, where we have dp dz of p plus rho gamma z, and that equals 0. So we simply, as we've seen before, this gives us our piezometric equation. This is just a hydrostatic equation, in fact. This came as a result of the hydrostatic equation, and we can simply write this as, let's use let's use 0.2 as being, again, if I go back to the figure here, let's use 0.2 as being up here, and this is being 0.3, And so what we'll find out now when we write this equation down is that we have P3 plus gamma Z3 minus P2 plus gamma Z2, and that is going to equal 0. And we can then solve for P3. This is going to equal, now let me just back up just 1 second here. Let's just write this out. Let's just write it out like this. Equals P2 plus gamma Z2, and so P3 is going to equal P2, which was our 261 PSF. That's the pressure at the top, and this is going to be plus gamma Z2 minus Z3. This distance from Z2 to Z3 is just the height of the fluid. And so if we plug in now for P3, this is 261 PSF, and we're going to be just adding gamma, 42 lbf, pound force over foot cubed. That's our gamma, and that's just going to be merely times 6 feet. And so when we calculate this term out, it's going to be, it looks like it's about 250 or so. And we notice that the units are going to be in PSF because this cancels this and leaves a square foot here. So that's pounds per square foot PSF. And our final answer turns out to be 531 PSF. So what we've determined is that the pressure basically of the fluid above the point at the front of the trailer basically doubles the weight at the front. So remember that the PSF, the pressure due to the deceleration at the front of the trailer, is 261, and now at the bottom of the trailer we have 531 PSF. So we can see that just the weight of the fluid is doubling the pressure at the bottom of the tank. Okay, so I hope that makes sense in terms of these two examples and how we can apply the Euler's equation to solve some pretty interesting problems. Okay, thank you.